we're going to talk about prime factorization. And before we can talk about prime factorization, we've got to define prime numbers. Prime numbers have only two factors, 1 and the number itself. So let's just put an aside here. 1 is not a prime number because it only has one factor. So I have only underlined here, but it should be exactly. That would probably be a better way of saying it. Prime numbers have exactly two factors, 1 and the number itself. So let's go ahead and make a list of some of the beginning prime numbers. And by beginning, I mean from whole numbers, starting with 0 and going up. 1 is not a prime number, 0 is not considered a prime number. 2 is the smallest whole prime number, and it is the only even prime number. 1 and 2 are the only factors of 2. 1 and 3 are the only factors of 3. 1 and 5 are the only factors of 5. 1 and 7 are the only factors of 7. The next odd number is 9, but it's not prime because it has a factor of 3. So it has more than 2. 11 is a prime number. 13, 15 is not, because it has a factor of 3 and 5, as well as 1 and 15. 17, 19. And then as we go on, our prime numbers become further and further apart. 21 is not a prime number because it has factors of 3 and 7, but 23 is. 25 is not a prime number. 27 is not a prime number, but 29 is. 31 is a prime number, but 33 is not. So here are just some of the beginning prime numbers, and it's important to understand the definition. Exactly two factors. Now, let's look at prime factorization. Prime factorization is expressing a number as a product, and product is the answer to a multiplication problem, of the prime numbers. So prime factorization is different than a list of factors. A list of factors, you are recording every single number that goes in evenly into that number. Prime factorization, however, you're only looking at the prime numbers. And there's a reason for this. This makes some other math very, well, easier and doable further down the line. So it's important that we know how to do this. And the easiest way to do prime factorization is to use what's known as a factor tree. And a factor tree looks like a Christmas tree. And the very apex, the very top of the tree, is the number itself. And from that number, we have two branches, and we keep on going until the end of each branch is a prime number. So let's start with 18, since we've already looked at its list of factors. Let's look how it is different when we prime factor it. So we want the prime factors of 18. That's what we're trying to solve here. So we're going to prime factor the number 18. We start with the number that we're given at the very top of our tree. And then what we have to do is we draw these two branches. And these two branches, at the end of each branch, have to be two factors of 18. So that's why it's important to know your divisibility rules. Sometimes if you're given a big number, it's helpful to have a starting place using your divisibility rules. Now, what two factors should we choose? We do not want to choose 1 and 18. 1 is not a prime factor, and we're trying to get 18 into only prime factors. So we never ever use 1 and the number itself when we prime factor. Now, aside from that, it really doesn't matter what two numbers we choose, and I'll go through the prime factorization two different ways so you can see it doesn't matter which two factors we choose. The only rule is that these two numbers must multiply together to be this number, and of course they can't be 1 in the number itself. Now, after we write these two numbers, we ask ourselves, are these prime numbers? Well, 2 is prime, so I'm going to circle it just so I can keep track of it. If you have a highlighter, it's a good idea to highlight your prime numbers. It's easy then to go back and find them. 9, however, is not prime. What are its two factors besides 1 and 9? 3 and 3. And 3 is prime. So I have just prime factored 18. When the end of each branch is a prime number, we're done. Now, how do we express the answer? The answer, we look at each prime factor and we express each prime factor as a base. So 2 times 3 to the second, since there are 2 3's here. And remember, I have an invisible 1 up here for my 2. If there's only 1, we know that that's 2 to the first power. So this would be the answer for prime factoring 18. These are only prime numbers, and if I check my work, 3 squared is 9, 9 times 2 is 18. The answer down here needs to equal this answer up here. Now what if I chose 3 and 6 instead? We'll get the same answer. As long as you do your math correctly throughout the factor tree, it doesn't matter what two factors you begin with. So here's 3 times 6. 3 is prime, but 6 is not. Since it's even, I know that 2 goes into it, and it goes into it 3 times. Now, I have prime numbers. So to write this out, each prime number is its own base. I have 2 3's, and again, if I check my number, 2 times 9 is equal to 18. So that's how we prime factor. Let's go through one example. That will also introduce us to a little shortcut. Actually, I'm not so sure it's going to introduce us to the shortcut. Let me do 1,000 and I'll come back to this number because this is an important number that will introduce us to a factor of 10 that I want to go over. All right, so where do we start? Well, this ends in all zeros, and I know that anything that ends in 0 is divisible by 10. And 10 goes into 1,000 100 times. 10 is not prime, so I have to keep on going, but 2 and 5 are prime, so I can stop there. Now 100 has several different pairs of factors. I'm just going to start with 4 and 25. You could have started with 10 and 10 or 50 and 2. It doesn't matter. Neither one of these are prime, so I have to keep on going. I must prime factor 4 and 25 since neither one are prime, but after I factor them, they are prime. Now, I have 1, 2, 3, 2, so I have base 2 cubed, and I have 1, 2, 3, and if I check my work, 2 cubed is 8, 5 cubed is 125. 8 times 125 is 1,000. Definitely want to always check your work. All right, now, I was interested in looking at 1,000 because there's no other way for me to say it except beautiful, way of factorizing these powers of 10. And by powers of 10, I mean numbers that begin with 1 and then just have zeros after them. These are powers of 10. If I take 10 and multiply it by itself 3 times, I will get 1,000. And one of the beautiful things about this is when I'm looking at what my exponent is, all I have to do is count how many zeros I have. Let's look at 1,000,000. What power would I have? 1, 2, 3, 4, 5, 6. Now, a lot of times in our everyday life, we're told to avoid shortcuts because it can lead to errors. But in math land, sometimes we really want to use shortcuts because time is money. And if we have a shortcut that always works, it can help us figure out an answer quickly or estimate to see whether an answer is wrong or not. So I encourage you to get used to these shortcuts. They'll save you time and hopefully make math more fun.